So this is an example for if you're asked to work out what the total pressure is. And yes, you'll be given kp, and you'll be given some either initial moles or equilibrium moles or something like that. And when you're working out the partial pressure, so that's when your total pressure comes into your calculation. So when you're working out your partial pressures, what is partial pressure?
What do you mean, what is it? It's P total on something.
Mole fraction times your total pressure. So that's when we use our total pressure in our our kp calculations. So when we get to the stage of working out partial pressures, we just take the total pressure as P, or P total. Okay, so let's have a look at this example, and hopefully that will help us. Okay, so we see your examples there, but look what it says. A 50% conversion of sulfur dioxide to sulfur trioxide occurs. What does a 50% conversion mean? We saw this.
Half the moles.
Half the moles what?
Converts.
Half the moles react. So I want you to write that in. It means that 50% of the initial SO2 moles reacts. Or react. Okay, and we saw that with KC on page 21 with percentage conversions. So the first thing I want to work out before I start my calculation are the reacting moles of sulfur dioxide. So I know that 50% of them reacted. So the reacting moles so to take a percentage of something, you do the percentage, so it's 50% over 100 times by the initial moles of sulfur dioxide, which is 2. So it's 2 moles of SO2. So it's 50%, which is 50 over 100 times by your 2. So how much of my SO2 reacted?
100.
What's 50% of 2? 1 mole. Okay, now I'm ready to write out my working out. Okay, so I'm going to write my equation out first of all. SO2 plus O2 reacts to give me 2SO3. And there should be a 2 in front of that sulfur dioxide as well. Okay, so down the side I write what I have done this whole time, which is initial moles. What comes after initial moles? What comes after reacting? What comes after equilibrium moles? Mole fraction. And what comes after mole fraction?
Partial pressure.
Partial pressure. Leave a wee bit of space before partial pressure. Okay. The working out, which you'll probably not do anyway. Okay, what are my initial moles of sulfur dioxide? 2. Initial moles of oxygen? Initial moles of sulfur trioxide? 0. Always 0 for your products. Reacting moles, which one do I know? The one of sulfur dioxide. We worked out that 1 mole reacts. So what do I write for my reacting moles? -1. And then I use my ratio to get the other reacting moles. So what's the ratio to oxygen?
0.5.
What's the ratio to oxygen? 2 to 1. So that means it's -0.5. Ratio to sulfur trioxide is 2 to 2, or in other words,
1 to 1.
1 to 1. So it's going to be +1 because we're producing sulfur dioxide. Equilibrium moles is initial plus reacting. So what are my equilibrium moles of sulfur dioxide going to be?
Just the same, really.
1. 2 minus 1 is 1. 1 minus 0.5 is 0.5. And my equilibrium moles of sulfur trioxide are 1. How do I work out mole fraction?
1 over the total.
1 over the total moles. So I need to do my total moles first of all. So I'll do that over the side. So the total moles
What do you like?
is
2.5.
1 plus 0.5 plus 1, which is 2.5.
Moles.
Is that okay? Just totaling up my equilibrium moles.
It goes from 1 to
Did you want to
0.5.
make
Pardon?
How is it 0.5?
For oxygen, because your ratio of sulfur dioxide to oxygen is 2 to 1. So I have twice as many reacting moles of sulfur dioxide as I do to oxygen.
Well, how did it go down? What, like 1.5? Oh, because it's my fault. Never mind.
1 minus a half is a half, yeah. Okay. Have you got the total moles down? Can I zoom back in? No. Okay, so mole fraction of your sulfur dioxide is going to be 1 over your total moles, which is 1 over 2.5. 0.5 over 2.5 for your oxygen, and 1 over 2.5 for your sulfur trioxide. That works out as 0.4 for sulfur dioxide, 0.2 for oxygen, and 0.4 for sulfur trioxide. What did we say partial pressure is equal to?
Well,
Mole fraction
times pressure.
times the total pressure. I don't know what the total pressure is. I want to work out the total pressure, so I represent it just by a capital P, or P total if you want. So the partial pressure of sulfur dioxide is going to be 0.4 P.
Stand through the rest.
Partial pressure of oxygen is 0.2 P. Are we? Okay, and then for sulfur trioxide, it's going to be 0.4 P. If you want, write in P total, if that helps you. So we're at the stage now of writing these, putting these partial pressures into our expression for Kp. So in order to do that, we need to write our expression for Kp. From our equation, we can see that Kp is going to be equal to the partial pressure of sulfur trioxide squared, because it has a balancing number of 2 in front of it, over the partial pressure of sulfur dioxide squared, again because it has a balancing number of 2, multiplied by the partial pressure of oxygen. So at this point I'm just subbing in my values for the partial pressure, which I can see above. And so the partial pressure of sulfur trioxide is 0.4 P total. You don't have to put the little total bit at the end, but just if it helps you differentiate between the partial pressure and the total pressure. And that is going to be squared. And on the bottom we're going to have again the partial pressure of sulfur dioxide is 0.4 P total, again squared, times by the partial pressure of oxygen, which is 0.2 times your total pressure. And the question tells me that Kp is equal to 0.125. So I want to simplify this down a little bit, and what you can do is you can multiply out your brackets, multiply these all together. But what we can see is that we have something that's common on the top half of the equation and the bottom half of the equation. So here we have 0.4 P total squared, and here we have 0.4 P total squared. And because that's multiplied by our 0.2 P total, we can actually just cancel these out. If you want to multiply it out and everything, that is fine, but this makes it a little bit simpler. So once we get to this stage, once we cancel those out, we end up with 0.125 equal to 1 over 0.2 P total. And that's because I've cancelled those other factors. At this stage, it's a case of cross multiplying and bringing this over to the other side of the equation. So it's divided on the right hand side, so when I bring it over it's multiplied, and so it becomes 0.125 multiplied by 0.2 p total. Now that I've brought that to the other side, and that is equal to 1. Multiplying out that bracket, 0.125 times 0.2 is 0.025 p total, and that is equal to 1. And now to find p total, I just need to bring that 0.025 to the other side of the equation. So p total is 1 over 0.025, which equals 40. And at this point I need to think about my units for pressure. Units for pressure can be in atmospheres, they can be in kilopascals, they can be in Newton per square metre. But look to your kb value in the question. Kp is 0.125 atmospheres to the minus 1. So we know it has something to do with atmospheres. And so that means the units of our total pressure are atmospheres. It may be in kilopascals, it may be in newtons per square metre. You need to go back to your original Kp value to work out what the units are. So the next example is exactly the same. So have a go at example 2 on page 46, and then I'll go through it afterwards. So pause the video, give it a go yourself, and then you can play it to see if you get the right answer and also to go through it. So this second example is exactly the same. The only difference is that it asks us for the total pressure and then also the partial pressures of dinitrogen tetroxide and nitrogen dioxide. But we'll do it exactly in the same way, work out our total pressure first and then use this to find out our individual partial pressure values. The first thing we're going to do is write our equation, and then we can write all our working out underneath. So our writing down our left hand side, we write first comes initial moles. After that comes reacting moles. After reacting moles comes equilibrium moles. In partial pressure examples, we come next to mole fraction. Leave a bit of room for your working out, and then the last thing is partial pressure, which we put into our expression for Kp. So the first thing we work with is our initial moles, and we can see that initially we have 1 mole of dinitrogen tetroxide. And nitrogen dioxide is our product, so it's going to have initial moles of 0. We're told in the question then that the equilibrium moles of nitrogen dioxide is 0.6 moles. So that goes in the equilibrium moles section of nitrogen dioxide. We then can tell that our reacting moles of nitrogen dioxide must be plus 0.600. And then we can work out our reacting moles of dinitrogen tetroxide using our ratio, which is 1 to 2 in this case. So we need to divide our reacting moles of nitrogen dioxide by 2, and we get the reacting moles of dinitrogen tetroxide as minus 0.300. Equilibrium moles is initial plus reacting, and so 1 minus 0.3 is 0.7, and we've already got our equilibrium moles of nitrogen dioxide as 0.6. Mole fraction then is your number of moles over the total number of moles. So I need to, off to the side, work out my total moles. Total moles is going to equal 0.7 plus 0.6, which is 1.3. So in order to work out our mole fraction of each of these, the mole fraction of dinitrogen tetroxide is going to be 0.7 over 1.3, and that is equal to 0.53846. And the mole fraction of nitrogen dioxide is 0.6 over 1.3. which is equal to 0.46154. Partial pressure is the mole fraction times by the total pressure. I don't know what the total pressure is, so I can just use P to represent that. So partial pressure of dinitrogen tetroxide is going to be 0.53846 times by my total pressure, which is P. And for nitrogen dioxide, it's 0.46154 times by my total pressure, which is P. Now I'm ready to sub these into my expression for Kp, because it's partial pressure values that we put in there. So first I need to write my expression for Kp, which I do using my equation. Kp is equal to the partial pressure of nitrogen dioxide squared, because it has a balancing number of 2, over the partial pressure of dinitrogen tetroxide. Subbing in my values, the partial pressure of nitrogen dioxide is 0.46154 P, and that's all squared, over 0.53846 P. That's the partial pressure of dinitrogen tetroxide. The question tells me that that is equal to 3.89. The Kp is 3.89. Multiplying out that squared and multiplying out my bracket, I look at what my number is squared. So 0.46154 squared is 0.213019 P squared. So I square my number separately and then square P, so that's obviously P squared. And that's all over 0.53846 P. Okay, I can cancel down this fraction a bit by taking my numbers first of all and dividing them by each other. So doing 0.213019 divided by 0.53846. That gets me 0.3956. And then I can divide my p's down separately as well. So I've got p squared divided by p. You can imagine that has an indice of 1 to the power of 1. And when I'm dividing indices, just like we do with our units, we take them away from each other. So 2 minus 1 is 1, so it's just 0.3956 p. So p squared divided by p is just p. And again, that's equal to 3.89. So now I want to rearrange my equation to try and get P. To do that, I do 3.89 divided by 0.3956, bringing it over to the other side by dividing. And so what I work out is that P is equal to 9.83. Again, I look to my units of Kp and see that they're in terms of atmospheres. And so the total pressure must also be in atmospheres. So the total pressure is 9.83 atmospheres, which is the first part of the question. But you'll notice that the question asks you for the partial pressure of your two substances in the equation. So firstly, the partial pressure of dinitrogen tetroxide. At equilibrium, we said that was equal to 0.53846 P. And we sub in the value that we've just worked out for P. So it's 0.53846 times 9.83 and 296. I'm just going to add a few extra decimal places to make this a bit more accurate. That's what our more accurate value of P was before we cancelled it down to 9.83. So multiply that out and you should get that the partial pressure of dinitrogen tetroxide is equal to 5.29 atmospheres. Then the partial pressure of nitrogen dioxide is equal to 0.46154 times the total pressure. which is 0.46154 times 9.83296, which equals 4.54 atmospheres. So there you've worked out the total pressure and also the partial pressures of your dinitrogen tetroxide and your nitrogen dioxide. But in order to do that, you had to work out what your total pressure was first. So now you're at the stage you can complete your 10 questions over on page 47 and 48. So have a go at those and let me know if there are any problems.